So for today's class, we're looking at oxidation and reduction, right? Now, earlier we had looked at types of reactions where you learned about single displacement, synthesis, and different types. For oxidation and reduction, usually they will put the two together. You'll hear about redox reactions. All right, so you may hear or read up on and you see redox reactions. So all they did was to put the two together. So RED is for reduction and OX is for oxidation. Now we need to look at what exactly is oxidation and reduction. When you were learning, I said that we're going to touch it because it's a topic by itself, because what you'll find out is that oxidation and reduction can take place within the other types of reaction that you had learned. So we're going to look at some fun facts first. All right, so for this class, we're sticking to the first from objective from your syllabus. It says to define oxidation and reduction. We're defining it in terms of loss and gain of electrons, a change in oxidation state. Then for continuing class for the rest of the week, we're going to move on to identifying redox reactions. So today we're just sticking with 6.13. So did you know that combustion reaction converts energy stored in fuels into thermal energy? Next one. Did you know that corrosion of metals is a natural process that seeks to reduce the binding energy of metals? Fun fact number 3, did you know that metabolism of your food by the body converts the fuel in the food we eat into energy needed to power everything we do? Next one, did you know that batteries supply electrical energy? All right, now what do all of these have in common? Actually, they are all redox reactions, right? They involve oxidation and reduction. So the question should come to you now, what exactly is oxidation and what is reduction? Now, this table pretty much sums up the definition for redox reactions. In your reading, you're going to find that you find varying definitions. But what has happened is that over the years, the definitions are modified. So back in the day, they looked at oxidation as the gaining of oxygen. And of course, you can see the connection with the name. So if you think oxidation, if you do chem, even if you don't do chemistry, oxygen kind of comes to mind. And so to use the definition of oxidation is a gain of energy, right? You can kind of see where they're going with it. Now, reduction, they had defined earlier as the loss of oxygen. So gaining of oxygen was oxidation and losing the oxygen is reduction. But then they had realized something else, that similar process now occurred when you lost hydrogen, right? And so they modified the definition and came up with, okay, oxidation is when hydrogen is lost and reduction is when hydrogen is gained. But it was not satisfactory enough. So again, the definition was modified. Then they came up with this one now. Looking at the different types of reaction, and we have done different types of reaction, they noticed that electrons were being lost and gained. And so they defined oxidation as a loss of electrons and reduction as gaining of electrons. But is that always the case? No. And so we are now at this point where they define oxidation as increase in oxidation number and decrease in oxidation number. So what is going to happen? The first thing that you should notice, ladies, is that the processes are opposite. Where something is gaining, the other one is losing. So if oxidation has the gain of oxygen, reduction has the loss. If oxidation is a loss of hydrogen, then reduction is gain. So wherever you see loss for oxidation, reduction has gain. They're opposite in action. The other thing that you notice is that they tend to go hand in hand. Where you have oxidation taking place, you have reduction taking place. Hence, they came up with redox reaction because it occurs simultaneously. Now, we're going to look at the two older definitions first. I'm going to explore those first, but then you notice that the last two definitions are in bold. And those are the two definitions that we use today in identifying redox reactions. All right, so let's quickly look at the old definition, and then we're going to dive down into the correct definitions, and that's what we're going to practice because that's what we're going to use. So the old definition, the first one says oxidation is the gain of oxygen, right? So it's the addition of oxygen to a reactant. Let's explore the first one. In the first example, we have iron reacting with oxygen. What is being produced is iron 3 oxide. So iron reacting with oxygen to produce iron 3 oxide. Immediately, ladies, you can see iron, right, an uncombined element, now picks up or has gained oxygen atoms. This is straightforward. And so they termed this oxidation. So your uncombined metal here picks up on your oxygen. It gained oxygen. Another example is such where you have combustion, right? How do we know it's combustion? Because our only products are carbon dioxide and water. So for combustion reaction, notice that carbon in this case, right, has picked up on oxygen to produce carbon dioxide, to form carbon dioxide. So this is another example of the old definition, when one of the reactants picks up on oxygen or gains oxygen. But again, do all reactions in chemistry just involve, okay, reacting with oxygen? No, right? Now, the opposite said that reduction was removing oxygen. So this is it. Our iron 3 oxide that we formed when reacting with carbon. Look at what happens. My iron 3 oxide is now stripped of the oxygen. The oxygen has been removed, and so we now just have iron itself being formed. So that is what they were looking at in terms of redox. Then they noticed that, okay, they need a broader definition. All right. Now, when we look at oxidation and reduction, there's a definition, but then there's an acronym that can be used, which is known as oil rig. Right? It's separated now, but you can put them together. In many, many readings, you see them have this oil rig. And it's just an easy way for you to remember the definition. So oil oxidation is loss of electrons. Reduction is gain of electrons. Now let us see how that definition works with different types of reactions. So let's look at this, for example. Magnesium reacting with chlorine. All right, so we're going to go back. We're going to dig back a bit. We're going to go back to the days when we were looking at bonding. All right, let me know if you're seeing the white screen.
Yes, miss.
All right, awesome. All right, so we're going to go back to grade 10 with bonding. All right, so in grade 10, we'll ask you, okay, show the bonding between magnesium and chlorine. That is what we say to you. So we're not asking you to write a reaction, you know, we say, okay, draw a bonding diagram to show the reaction between magnesium and chlorine. All right, now, first of all, what type of bond would magnesium and chlorine enter in? What type of bond would they enter in?
Ionic.
All right, let's go back to basics. How do you know the different types of bonds? Tell me the types of bonds that you know. All right, good. Now I'm getting answers. So we know of ionic, we know of covalent, right? We also know of metallic. Of the three here, which one is appropriate for magnesium bonding to chlorine?
Miss
Ionic.
Ionic.
Ionic, all right. Why is it ionic? What does ionic involve?
A non-metal and a metal.
Very good. So ionic involves a metal plus a non-metal. Where's the metal? Which one is the metal? All right, so magnesium is the metal and chlorine is the non-metal. So let us go back. Now I'm going to use the dot cross method where we just write the symbol. All right, so we just write the symbol and we're going to place the number of valence electrons, right, around the symbol. So magnesium is in group 2, and so it will have 2 electrons on the valence shell. All right, now chlorine is in group 7, and so we're expecting 7 electrons on the outer shell. All right, now somebody tell me what is going to take place here. How would this bond occur?
Miss, magnesium will lose its electron.
Very good. So magnesium is going to lose its electron, but let's dig deeper now. So magnesium has 2 electrons to lose. Can these 2 electrons be transferred to this one chlorine atom?
No.
Another chlorine atom.
All right. Very good. So if I transfer this electron, I can only transfer 1 because chlorine only requires 1 additional electron to become stable. Now, what is recommended? Someone was telling me a while ago that we were to draw another chlorine atom. So what is happening is that 2 chlorine atoms would be required to, right, to take on these 2 electrons that magnesium is giving away. All right, now we don't stop there for the bonding diagram for ionic bonding. Now, if our elements or atoms have lost or gained electrons, we now form ions. All right, so magnesium now has a charge of 2+ because it has lost 2 electrons. And chlorine, right, each of them has lost 1 electron, has gained 1 electron, sorry, and so acquires a single negative charge. However, how many chloride ions are being formed? 2. Seen it? So how do we tie that in now with our definition? All right, so our definition says that oxidation is loss of electrons and reduction is gain of electrons. Our example was the bonding between magnesium and chlorine. So we have just done the bonding diagram here. Which species actually lost electrons?
Mr. Magnesium.
The magnesium. So by definition, if magnesium lost electrons, it meant that magnesium underwent oxidation. And if chlorine is the one accepted, so chlorine gained electrons, right? Then by definition, chlorine underwent reduction. All right. So that's just looking at one of the definitions in terms of loss and gain of electrons. So that's all we have to do. All we have to do is to look at which species is losing electrons, which one is gaining electrons. All right. Now let's look at this example. It's a different one. It says that, so, yes, darling?
Is the reaction before you would consider that as a redox reaction, since both
This would be a redox reaction because once a magnesium is losing, chlorine is accepting or gaining. So once you have loss and gain of electrons during the reaction, then it is a redox reaction.
Miss,
All right.
Miss, I have a question. If we were to identify the reaction and I write either redox or synthesis, I will still get it correct, right?
All right, so in a case like that, you won't be necessarily asked to say, okay, identify, like given this, you want to be asked to identify the type of reaction. All right, so later down, when we get deeper into the topic, you're gonna see where redox really fits in. All right, so as I said to you before, redox kind of span the different types of reactions. So later when we get into the topic, right now it's just an overview of just looking at the definition. So you see exactly where it fits in to this whole types of reactions, all right? All right, so let's look at example number 2. So we're still using magnesium, but then guess what? This is not a synthesis reaction like before. So magnesium directly bonding to chlorine is a synthesis reaction. This is not a synthesis reaction. This one now has magnesium reacting with hydrochloric acid. So I'm bringing up my whiteboard again. All right, so let's write that down now. So the reaction here is magnesium reacting with hydrochloric acid. And we know this reaction because we just did acid and bases. And acid reacts with a metal, right, to form salt and hydrogen gas. So if I am reacting it with hydrogen chloride, what salt am I producing?
Miss magnesium chloride.
Very good. So I'm producing magnesium chloride and hydrogen gas. All right, now for this type of reaction, it is not as easy to just readily pick up, okay, what species is being lost and which one is being gained. But then there is a type of equation that we wrote, right, that could expand and tell us now what were the ions involved. So what equation am I talking about? We're talking about writing ionic equations. So let us try that. So magnesium is a solid state here. Am I going to change this or write this out into an ion?
Mr. Gonna make it stay as it
Very
is.
good. This is going to remain. And then I'm going to split my acid. Oh, by the way, what is it that I forgot to do before I move on?
It's right, the charge of magnesium.
No, man, before I get to the ionic equation, there's something I forgot to do in the first line. And I always tell you girls, ensure. Go again? Someone was saying it. Balance. I forgot to balance it. So can we balance this before we get to the ionic equation, please?
Miss, just put the 2 at HCl.
Beautiful, beautiful. So that's all we needed, 2 at HCl. All right, so this now makes me have 2 hydrogen ions plus 2 chloride ions. So I'm writing out my overall ionic equation. All right, this is aqueous. This is aqueous. Are we doing anything to hydrogen?
No, miss.
No, very good. So we are letting hydrogen remain. All right, our next step is to do what? Eliminate our spectator ions. Do we have any?
Yes.
It's 2Cl.
Very good. So our chlorine is our spectator. So we are now left with this magnesium plus so this now, ladies, this is our overall net ionic equation, right? Now, what are we going to do with this? Our ionic equation actually tells us when a species actually gain or lost electrons. All right, so I'm going to pull out magnesium from the equation.
Miss, why you
Esther?
cross out chloride? The two chloride.
Because it remains the same on both sides, and so we call it the spectator ion. It doesn't change.
Okay.
All right. All right, so what is changing? So let's pull magnesium out of this equation, ladies. So on our reactant side, we had MgS, right? This means that I had solid magnesium. This is magnesium in the elemental stage, right? So I have atoms of magnesium. Now, on my reactant side, I have Mg2 plus. Now, what has taken place for magnesium to go from the atom to the ion Mg2 plus?
It lost
Is it that it loses the 2?
Very good. So what has happened is that magnesium has lost 2 electrons. See that? So magnesium has actually lost 2 electrons. So if magnesium is losing electrons, what has magnesium undergone? Oxidation or reduction?
It's oxidation.
Oxidation. Very good. All right. So now you see where you can start using your ionic equations. All right.
Excuse me,
No.
miss.
Yes, darling.
Miss, when the number is at the top, that means it lose. And then like
No,
when
hold on. When the number is at the top, if you have a number with a charge at the top, it means that an ion has been formed.
Miss.
okay.
I'm listening.
Okay, never mind. You just answer.
Right. So I don't want you to say when the number is on top, because remember now, you can form 2 types, negative and positive. So just to be safe, when you have the symbol with a number and a charge, it means that that's the ion. When you have the symbol only, no charge, nothing, just a state symbol, then that tells you that it is the element, it's in the elemental stage. All right, so I am just going to, no, I don't want to clear the canvas.
Excuse me, miss.
I'm listening.
Miss, you could look at it in terms of the hydrogen. Like what you was.
We're getting there, man. We're getting there. I just cleaning off the space, that's why. And persons had questions. All right, we're getting there. We're getting there. I know where you're getting at. All right, let's do this one quickly now. So hydrogen. So we did magnesium. So this is magnesium. Now we're going to pull hydrogen out of the equation, right? I'm going to change the color ink so that you know where I'm at. So 2H plus, right? And then on my reactant side, I now have H2. Now, if I am an ion and I'm going back to the element, so look at the ion. The ion here is a positive charge, and I'm going back to the element. What is it that happened that caused me to revert? So if I'm an ion and I formed a positive charge, did I lose or gain electrons?
Lose electrons.
You lost electrons. Very good. So to go back, to revert, what will have to happen?
Reduction.
reduction. I'm going to have to gain
to
back
gain
the
it.
electron.
Yes.
Very good. So because I have 2 hydrogen ions, right? Each will require one electron, and so in total I have 2 electrons. So in this case, hydrogen gained 2 electrons to form hydrogen gas. So the process that is taking place here now is reduction. All right, with me so far?
Miss, come again there, please. Come in our one the coral.
All right, so what we did in this case, so the equation is magnesium reacting with hydrochloric acid, right? But in order for us to say, okay, electrons lost and gained, it's easier if we wrote the ionic equation. So that is what we did. So here we have our net ionic equation. Magnesium in the solid state reacting with 2 hydrogen ions, right, to produce magnesium ion and hydrogen gas. That is our ionic equation. So what I did was just to split it in 2. I took out what were magnesium, and I examined what change is magnesium undergoing. So magnesium in this case, right, lost 2 electrons. So magnesium lost 2 electrons to form magnesium ion. By definition, if the species loses electron, then oxidation is taking place. Now I'm looking at the other half of the equation. Hydrogen ion gains 2 electrons. So we have 2 of them, you know. So in total, 2 electrons are gained to form hydrogen gas. By definition, if the species gains electrons, then reduction has taken place. So to identify, all we need to say magnesium is being oxidized and hydrogen is being reduced. Now, Manning was looking at the old definition, right? So she's saying that, okay, can we look at it in terms of hydrogen? Tell me your line of thought before I tell you mine.
Lisa was saying, since the hydrochloric acid is losing its hydrogen, then it would be using.
All right, and then how would you define oxidation?
Lisa, I don't know.
All right, so I how do you express it, because it's the same thing that they're saying, right? If you were to use the old definition, they're kind of restrictive, because not all equations will involve oxygen, not all will involve hydrogen, but it doesn't necessarily mean that redox is not taking place. Oxidation reduction is taking place. So that is why they had to broaden the definition. So I like that you're trying to use the old definition to say, okay, let me use hydrogen because hydrogen is involved. So they said that if the species loses hydrogen, then it is reduced. And if it gains hydrogen, then it is oxidized. But then this one is kind of funny, because really and truly, when you look on it, you're not seeing anything really gaining hydrogen except for, no, you're not really seeing it. And then oxygen is not there. So that is why they stay away from, not to say that you can't use it in instances, you know, because there are some definitions, some equations, sorry, or some reactions that right away you can see that, okay, this is what is taking place. Loss of oxygen, loss of hydrogen, and you can pick it up. But in an equation like this one, though you're seeing hydrogen, it is still not as clear what is taking place. And so it's best to use your loss of electron, gain of electron definition, or what we're going to explore in Thursday's class, which is looking at oxidation numbers. All right, so let's see if we are correct. See, magnesium is oxidized and the hydrochloric acid is reduced to hydrogen. So you could readily pick up the hydrochloric acid being reduced because it has lost the hydrogen. But then remember, we want redox. It's not as easy to see that, okay, magnesium now, because magnesium is not gaining or losing hydrogen or oxygen. So that's why we had to expand the definition. All right, good. Now, before we leave, I want to bring you back to this and a term that you must learn. So the term is this. It is known as half equations. All right. So this is a term that you must learn, half equations. Now, what are half equations? Half equations are this that we just wrote. Pretty much what you're doing is taking out one species out of the reaction. So remember, you have A and B. So we're splitting the reaction in two. We're taking species A and telling exactly what is happening to it in terms of losing and gaining electrons. And then we're taking species B and telling you what exactly is happening. So these are half equations, ladies. So where we have showing magnesium losing the two electrons to form magnesium ion, that's one half of this equation here. And when we show hydrogen gaining electrons to form hydrogen gas, that is the other half of the equations. So keep this in mind because it comes up in electrolysis as well when they speak of half equations. All right. So we will pause here. All right, you can go home, read up on it. You have textbook, you have the rental book, you have the book that I posted online. You are going to read it over, and on Thursday, we are going to look at our next definition, which looks at redox reactions in terms of oxidation numbers. So if you do not remember what an oxidation number is, I'm going to advise you, right? Go and look it up. Find the definition for the term oxidation number. If you do not see oxidation number, then look for oxidation state.
Miss, how soon will you post the recording?